This equation shows an ionic bond being formed. On the reactant side we have the elemental form of both of these elements, and what happens is sodium prefers to lose one electron and chlorine prefers to gain one electron. In that case, both will have a full outer valence shell, and what we get is sodium having a +1 charge and the chloride ion now having a negative charge, and those two charges are going to attract each other to form NaCl. Salts are brittle solids with very high melting points. The heat of formation, which is what that symbol means, delta HF naught, this is the enthalpy of formation for substances in their standard states. You can see that for this salt, the enthalpy of formation is negative, which means there is a great deal of heat or energy that is released in the formation of these bonds, which tends to make the resulting NaCl a very stable material. Now, the lattice energy is the energy that would be required to separate 1 mole of solid ionic compound into gaseous ions. And the lattice energy is a measure of the stability of the ionic bond. Here's an equation that illustrates the idea of lattice energy. We start with NaCl as a compound, and if we add heat to it, notice the positive sign on the energy, then we can form gaseous ions. And in general, ionically bonded substances have big positive lattice energies. In other words, we have to put energy in to separate these compounds into their gaseous ions, and typically we have to put a lot of energy in. Because lattice energies are electrostatic in nature, two variables are involved in how big they are. One, the absolute value of the product of the two charges, and two, the separation between the ions. In comparing lattice energies, always look at point number 1 first. If the products differ, stop. You have your answer. If the products are the same, only then consider point number 2. In other words, of these two variables, the first one wears the pants. Let's look at a couple of examples. Let's put the following in order of increasing lattice energy. From the periodic table, we can figure out the charge on each of these ions. Lithium is 1+, bromide is 1-. Here we can figure that because the nitride ion is 3-, this iron ion must have a charge of 3+, and then we know that cadmium's charge when it bonds with things is always 2+, and oxide is almost always 2-. The first thing we do is we look at the product of the charges, and for lithium bromide that product would be 1 times 1, which is 1. For iron 3 nitride the product is 9, and for cadmium oxide the product would be 4. Since those products differ, we do not have to consider the size of the ions. We simply say lithium bromide would have the lowest lattice energy and iron 3 nitride would have the highest. Lattice energy, of course, is related to things like melting point. So if we had to guess, we would say that of these three compounds, iron 3 nitride would have the highest melting point and lithium bromide would have the lowest. There are many other ionic compounds, and if we had to predict, we would say that something like, down here at the bottom, potassium oxide would likely have a lattice energy that lies somewhere between that of lithium bromide and cadmium oxide. And that's because the product of the charges for potassium oxide is going to be 2. Potassium is 1+, oxide is 2-, so that product is 2. Similarly, iron 3 oxide, we would predict, would have a lattice energy and a melting point somewhere in between cadmium oxide and iron 3 nitride, because cadmium oxide's product is 2 times 2 is 4, Iron 3 nitride is 3 times 3, that's 9. Well, the product of these charges, the charge on these iron ions is 3 plus, and the charge on each of these oxides is 2 minus, so 3 times 2 would be 6, which lies somewhere in between 4 and 9. Now let's put these in order of increasing lattice energy. So let's look at the charges. The first one, magnesium is 2 plus, sulfide is 2 minus. The next one consists of magnesium 2 plus, and each of the chloride ions is 1 minus. And then the last one, magnesium is 2 plus, oxide is 2 minus. So based on the charge magnitudes alone, we know that of these three, the lowest lattice energy is going to be the MgCl2. Now, what do we do about the magnesium sulfide and the magnesium oxide, because the charges there are the same? Well, now we have to look at the separation between these ions. So let's draw a picture and see if we can figure this out. Because of where they are in the periodic table, we know that the sulfide ion is larger than the oxide ion. So now let's put the magnesium ion in there, and of course it's the same size whether it's bonded to oxide or sulfide, because it's just a magnesium ion and it's got a particular size. And you can see here that the separation is different when the charges are closer, as they are in the case of magnesium oxide, compared to when they're farther apart, as in the case of magnesium sulfide. When the charges are closer, then that's going to be a larger lattice energy. So of these, we would predict that the magnesium oxide would have the largest lattice energy. Final thoughts on ionic bonding. Ionic bonding is the Coulombic attractive force between positive and negative ions. The lattice energy is a measure of the strength of the bond. The larger the lattice energy, the stronger the bond. 2. The magnitude of the lattice energy, i.e. the ionic bond strength, in an ionic substance depends on A. the magnitudes of the ion's charges, and B. the sizes of the ions. Ionic bond strength increases with increasing charge magnitudes and decreasing ion sizes.